Welcome. Thank you so much for being with us tonight. I'm your host, Sam Pasco, and tonight we start with the Trump administration. Wait a second, this isn't last week tonight. It's a chemistry research project. Let's start with my research question. What are various doping methods, and how are they tested for? Yes, so tonight's topic is doping. Doping has been a pretty widely known about topic in relation to athletics in recent years. You remember that Lance Armstrong was stripped of his 7 Tour de France titles because of doping, and Barry Bonds is still not in the Hall of Fame because of allegations. Russia's entire 2016 Olympic squad was banned from the Rio Games because of state-sanctioned doping. Even Mark Sanchez, yes, Mark Butt Fumble Sanchez, will be suspended 4 games in the upcoming NFL season due to banned substance contamination.
I've never seen this before in my life. Watch this. Vince Wilfork is going to throw Brandon Moore back into his quarterback.
Tonight we are going to clear up some misconceptions and talk about the chemistry of doping. But before we go any further, it's best we define some different terms, because doping is more or less a slang term. Doping is defined as the use of banned athletic performance-enhancing drugs by athletic competitors. PEDs, or performance-enhancing drugs, are also considered a form of doping, but can include various drugs, including stimulants, narcotics, and gene doping. Also note that when we talk about steroids, we are referring to anabolic steroids, not cortisoic steroids, which are hormones produced by your adrenal glands in the kidneys, which are used for rashes and autoimmune diseases. Tonight we'll focus on anabolic steroids, EPO, and blood doping, because they have the most connections to our various learning goals, even though there are other ways of doping. And now, Stewie from Family Guy on steroids.
I look like a guy who's been hitting the gym.
It has nothing to do with the gym. You're on drugs.
Doesn't matter how you find the pot of gold, beat to the rhyme. All that matters is that you beat the leprechauns.
That doesn't make any sense.
Doesn't have to make sense when you look like this.
Thank you, Stewie. First, let's take a look at anabolic steroids. Anabolic steroids are compounds that are developed to increase muscle size and strength. Typically, these steroids can be detected in an athlete's urine. We'll talk about testing later, but right now, you need to know that anabolic steroids are a type of lipid or fat molecule. Also, anabolic agents in general are the biggest class of prohibited drugs at the Olympics. In 2014, the World Anti-Doping Agency, or WADA for short, found that 48% of positive tests were due to the use of anabolic agents. So while taking anabolic steroids, you may end up like Steve Rogers.
Mr. Stark?
But there are many side effects which make them very unsafe. These side effects include high blood pressure, which can lead to heart disease, and also kidney damage. In both men and women, they can also have aesthetic effects as well. For men, they can shrink the testicles and enlarge breasts, as well as reducing sperm count.
You start taking steroids, this is what's gonna go down. Your face is gonna turn to the the pizza factory. Your back's gonna look like the Urals, the Himalayas, the Alps, and the Rockies are making love. Then in the front here where your bee bites are, you're gonna get some big, supple, delicious Jennifer Love Hewitts going.
In women, they increase body hair, decrease breast size, and deepen the voice. So what's this got to do with our learning goals from this year? Well, I actually have quite a bit to do with our learning goals. First off, anabolic steroids are structurally similar to the natural human hormone, testosterone, and when taken mimic its effects. In general, all steroids share the same basic 4-ring carbon structure, but differ when looked at specifically. A testosterone molecule is tetracyclic, or has a tetracyclic base structure. The structure consists of 4 separate rings of carbon atoms attached to one another. You remember this concept from Learning Goal 5.2. In terms of chemical properties, the arrangement of atoms in testosterone are quite stable. Given its large size, testosterone consists of very few reactive areas. The atom consists of mostly carbon-carbon single bonds and carbon-hydrogen single bonds, both bond types being largely unreactive because of the octet rule, which we learned about in Unit 5. You should also note that testosterone is composed entirely of carbon, hydrogen, and oxygen, which are all parts of the Brinkelhoff series, which we learned about in Unit 5. I can explain why the 7 diatomic elements, Brinkelhoff, form covalent molecules. Oh, the connections to learning goals don't stop there. These anabolic bad boys even include a little dimensional analysis, if you will. Let's take a look at a sample problem. Next up, we got EPO, also known as erythropoietin, which is another common method of doping. It's a hormone produced largely in the kidneys that influences the rate of production of red blood cells and thus the flow of oxygen to the muscles. Let me say it again. Instead of stimulating muscle development like anabolic steroids do, it regulates the creation of red blood cells and can do so at 25% above the normal level. This substance is then transported through the plasma in the bone marrow, where it accelerates the production of red blood cells. This can cause heart attacks, strokes, and possible shrunken testicles. EPO, along with blood doping, which we'll get to in a minute, pertains mostly to cyclists because of the endurance nature of the sport. The UCI periodically checks riders for the level of red blood cells in their blood, with the limit of 50% or 55% for riders from high altitude regions. Anything above that is regarded as an indication of the use of EPO and carries a 2-year suspension. The learning goal connection for EPO and blood doping are actually pretty interesting. If you remember back to Unit 7, we learned about Le-Chatelier's principle. This dude's principle even got him his own learning goal. I can explain Le-Chatelier's principle in terms of collisions and reaction rates. Well, with EPO, you can almost think about our bodies being that system in equilibrium. So when the number of circulating red blood cells decreases, or when oxygen transported by the blood diminishes, an unidentified sensor detects the change and production of erythropoietin is increased. This can happen when you go to a higher elevation or when you give blood. As for the unidentified sensor, scientists don't really know what tells our body to do this. For all we know, it could be those little guys in submarines that help fight diseases that could be doing this.
Maybe stick us in those submarines that they put in people's bodies to fight diseases?
Okay, that's not a real thing, the submarines.
No. Bottom line, the EPO mechanism operates like a thermostat, increasing or decreasing the rate of red blood cell production in accordance with our need. Keep in mind, this works both ways, just like a system in equilibrium did. When a person who has lived at a high altitude region moves to a sea level environment, production of EPO is suppressed, and the rate of red blood cell production declines until the red blood cell count falls to the normal sea level value. And if you didn't quite get our little nickel-sized joke by Vince Vaughn and Owen Wilson, let me put it this way. With the loss of 1 pint of blood, the EPO mechanism is activated. Red blood cell production is enhanced, and within a few weeks, the number of circulating red blood cells has been restored to the normal value. Blood doping is similar to EPO, but they are slightly different. They have the same goal to artificially increase the number of red blood cells in the body, and therefore oxygen available to your muscles, but they do go about it differently. While EPO forces your body to make more red blood cells, blood doping does it more manually, through direct blood transfusion with the athlete's own older blood.
Yes or no? Did you ever take banned substances to enhance your cycling performance?
Yes.
Let me explain. A few weeks before competition, an athlete draws out a few ounces of his own blood and freezes it. Like blood donation, your body will then make new blood after the blood donation. Before competition, the athlete then transfuses this older blood back into their body, giving them more blood and more red blood cells. This synthetically increases the number of red blood cells available. Similar problems arise from blood doping as with EPO. But what I didn't mention about EPO is that blood doping can be extremely dangerous because of the amount of red blood cells that are in your blood. Although both methods do increase the amount of red blood cells in the blood doping does so much more directly and in a way that the body can't keep up with the amount of red blood cells produced or injected synthetically. With the increased amount of red blood cells, it creates thicker blood, which forces the heart to work extra hard to pump this blood through the body, eventually leading to a possible stroke or heart attack. This principle is actually very similar to Learning Goal 2.1. I can explain the relationship between pressure, volume, and temperature of a gas using kinetic molecular theory, KMT. While we were talking about balloons in this unit, the body almost serves as the balloon with blood doping. If we increase the volume, in this case the volume of red blood cells, and the temperature stays constant, pressure will increase since there's just more red blood cells in the body in the same confined area, leading to them hitting each other more often. Alright, now that you have an idea of some of the different types of drugs used with doping, let's talk about some testing. So here's how it normally goes. An athlete takes a performance-enhancing drug, and it's injected either orally or injected straight to the blood. During a random drug test, the athlete is asked to donate a sample of his urine to science. The urine travels to a testing facility, where chemists in the facility introduce a sample of urine into an instrument that looks like 3 photocopiers put together. The instrument is an analytical tool known as a mass spectrometer. It tests the urine for the presence of steroids or chemicals that are produced as the body processes the steroid, which may be detected for days to weeks after the last dose, depending on when the drug was taken last and the amount taken. The lab informs the league of positive results, and the guy's busted. The really interesting chemistry here is in the mass spectrometer. But there are some very interesting details in how they test for recreational drug use, which we won't go into it too much in detail. But take a look at this video about how the cups work.
And in this video, I'm going to show you how to use drug test cups. Test Country offers a variety of cups with different key features. The teacup offers any combination of drug testing from 5 to 14 different drugs, plus adulterant.
The principles behind mass spectrometry can be a little abstract at first, so let's start with something concrete and a learning goal to start. If you remember back to Unit 1, our very first learning goal was measurement is a process used to estimate the value of a quantity, mass, volume, temperature, etc., using instruments that we've purposely chosen. We use this principle in probably one of the most dangerous labs of all time, the penny lab. We put various pennies in special cylinders that attended college, graduated cylinders, to see how much water they displaced, but also measured those pennies too. At least for my group, we did this in groups of 10, because weighing one penny or seeing how much water just one penny displaces wasn't too visible. So when we did this, we of course divided our results by 10 to get the weight or water displaced for just one penny. But what if instead of getting bigger, in bigger number of pennies, like 10, 20, or 100, what if we wanted to go smaller? We wanted to know just how much a single atom scraped from the chinny chin chin of Abraham Lincoln weighed. How would you measure this? Well, this problem was confronting many chemists in the beginning of the early 20th century. But whose work did they turn to in this time of need? Chemistry Jesus, of course, John Dalton. You remember him from Unit 3 on atomic structure. Learning Goal 3.2, the model of an atom is an abstraction that has been developed over time with contributions from both experimental and theoretical physicists. Thanks to John Dalton's atomic theory, they knew that matter was made up of atoms, and that atoms of one element were the same. Then, in 1887, the lesser-known Splash brother, J.J. Thomson, spelled with an M, by the way, no P, discovered the electron by studying the behavior of the cathode rays, the stream of negatively charged particles originating from the cathode, or negative electrode, in a gas-filled vacuum tube. A year later, another chemist by the name of Willie Wayne began working with positive rays, the stream of positively charged particles that came from the anode that moved towards the cathode. They observed that a magnetic field could be deflected by positive rays. Then, in 1907, Thomson began deflecting positive rays with both electric and magnetic fields. He discovered that he could determine the particle's mass by measuring how far they were deflected. So what's going on inside one of these mass spectrometers? To understand the basic principles of mass spectrometry, consider a person standing on top of a tower, but in a windy day. The person picks up various balls and drops them, one by one, from the tower. As each ball falls, the wind deflects it along curved paths. But the mass of the ball does affect how far they would fall. So if you were to drop a bowling ball, per se, it's much heavier than a basketball. so they're going to have different paths, and the wind's going to affect them differently. In a mass spectrometer, the same thing is happening, except it's atoms and molecules that are being deflected, and it's electric and magnetic fields that are causing the deflection. The machine that does this contains three basic parts: the ionization chamber, the mass analyzer, and a detector. Here's how they work together. To be deflected by an electric or magnetic field, an atom must first be ionized, or turned into a charged particle. This is actually a little bit of Unit 4 from our Learning Goal 4.1. Since metals and nonmetals have different strengths of attractions for their valence electrons, when they come in contact with each other, they can gain or lose electrons, thereby becoming ionized. This is accomplished by knocking away one or more electrons, which results in a particle with a net positive charge. Spectrometrists sometimes bombard a sample with a beam of electrons to ionize the molecules. The incoming electrons act like billiard balls, knocking away electrons in the sample. They also use this technique known as electrospray ionization, which forces a sample through a charged needle to strip away the electrons. Either way, the first step of mass spectrometry is to produce positively charged ions. Next, the positively charged ions must move out of the ionization chamber. The force required to move them comes from an electric field supplied by two metal grids. One grid is positively charged and repels the ions, while the other is negatively charged and attracts them. Because the repulsion and attractions act in the same direction, the ions move rapidly towards the negatively charged grid, which is perforated with many tiny holes. The ions then pass through the holes at varying speeds, lighter ions traveling faster than the heavy ones. Due to the laws of electromagnets, a moving stream of electrically charged particles will generate a magnetic field. The ions in a mass spectrometer are no exception. They produce a magnetic field of their own, and it is a magnetic field that scientists take advantage of in the most important step of mass spectrometry. Creating and accelerating ions are essentially preparatory work to the main steps of mass spectrometry: mass analysis. The main job of the mass analyzer is to apply an external magnetic field to the ions exiting the ionization chamber. This external field interacts with the magnetic field generated by the fast-moving particles, causing the path of each particle to bend slightly. How much an ion's path curves depends on two main factors: the mass of the ion and its charge. Lighter ions and ions with greater charge are deflected more than the heavier ions and ions with smaller charge. Chemists combine these two variables into a value called mass-to-charge ratio, which is represented mathematically as m/z, or m divided by E. For example, if an ion has a mass of 18 units and a charge of +1, its mz value is 18. Most of the ions moving from the ionization chamber to the mass analyzer have lost a single electron, so they have a charge of +1. That means the mz value of most ions passing through a mass spectrometer is the same as the mass of that ion. A computer is then used to analyze the data collected at the detector and displays the results on a graph known as a mass spectrum. On most graphs, the mass, measured in atomic mass units, AMU, is plotted on the x-axis. Relative intensity, which measures how many ions of a given mass are detected, is plotted along the y-axis. Now let's get back to sports. In mass spectrometry, the urine would be called a sample. Once upon a time, mass spectrometers could only analyze samples that existed as gases, but today's models can handle both solids and liquids. Scientists then insert the sample directly into the ionization chamber, or, if it's a complex mixture, into another device that performs the first pass separation of the sample's component parts. Chromography is the most common way to conduct this initial separation and can occur as either gas chromatography, GC, or liquid chromatography, LC. Chromatography separates the sample into a series of components by first dissolving the substance into a gas or liquid, then forcing it through a secondary material. A component that is soluble in the first phase will move much more slowly than a component that is not soluble in the first phase, but is very soluble in the second phase. As a result, the various components become separated. Each one enters the mass spectrometer for analysis. urine drug testing is typically conducted by a gas chromatographer / mass spectrometer, GC/MS. Sometimes, though, more than one mass spectrometer is useful in a technique called tandem mass spectrometry, which basically acts to break apart large ions into smaller ions for more detailed analysis. All of this is required because the urine contains a large number of components, including naturally occurring steroids. Using GC/MS or GC/MS/MS detects more chemicals and yields more reliable results. If you remember back to Unit 5, we actually worked with a gas chromatographer in our GC lab. That's what GC stands for. Specifically looking at Learning Goal 5.3, I understand the causes and relative strengths of each intermolecular force, IMF, including induced dipole, also called dispersion forces, dipole-dipole forces, and hydrogen bonding forces. So that's the basics of mass spectrometry. But how do they use it to test for illegal steroids? Well, actually, it's quite similar to our GC lab. First, they analyze several known steroids to produce their mass spectra for comparison purposes. They can also rely on tables of mass values if they are available for reference. Next, they analyze normal uncontaminated urine. They then test a player's urine using either GC/MS or GC/MS/MS. Finally, they compare the mass spectrum produced from the player's urine with the spectra of normal urine and known steroids. By comparing the peaks on the spectra, which represent ions of various masses, chemists can identify exactly which drugs, if any, are present in the urine. Boom, science. Notice that the test sample has peaks that line up with the steroid standard. The peaks represent ions containing certain elements. For example, the C2H3 ion will have different peaks than the OH ion. In this way, mass spectra are used as, quote, fingerprints to identify compounds. In gas chromatography, the sample is vaporized in the presence of a gaseous solvent and placed through a long path of a machine. Each substance dissolves differently in the gas and stays in the gas phase for a unique specified time, called retention time. Different retention times correlate to different drugs. Alright, that's our show for tonight. Hope you enjoyed yourself and learned about chemistry as well. I'm pretty sure we hit everything in the rubric, so make sure to give this project a score. A big thank you to Cindy Spivey, Cameron Nation, and James C. Sullivan for technical assistance. Also a big thank you to the chemistry department for letting us use this fantastic room. If you didn't understand anything that I said or wanted to fact check me, references, bibliography, and script will be available, so check the link in the description. Alright, thank you.